So my name is Terry Key. I'm an inorganic chemist at the University of Leeds School of Chemistry, and today I'm going to tell you a little bit about electrochemistry. Electrochemistry is a very important aspect of our lives. You've probably seen examples as you're walking around the street. Pieces of iron rusting. That's a very important example of an electrochemical process in action. And if you want to know more about that, then you can take a look at my earlier podcast, which introduces this in the aspect of electrochemistry. If we consider two metals, let's say we've got magnesium over here and copper over here, my left and right hands respectively, each of those metals has a different ability or different tendency to undergo oxidation and reduction. Now, oxidation and reduction are both examples of electron transfer processes. Reduction is the taking on board of electrons, the acceptance of electrons, whereas oxidation is the release of those electrons. There's more about that in my earlier podcast. Back to magnesium and copper. These two metals, if you put them in a solution of water, what you will find is that each of those two metals, they will gradually dissolve into the water and they will give up some of their electrons. What we find, though, is that the magnesium gives up more of its electrons than the copper, and that means there is a buildup of electrons on the magnesium electrode, as it's called. If we then connect those two metals via a wire, and we connect the two solutions via what's called a salt bridge, we have the basis of a battery, and electrons can flow one between the other. That process is extremely important, but what we need to do is we need to know which metal, the magnesium or the copper, is going to be more likely to give up their electrons. And we do this by giving a number to each of these metals. In fact, any species can have this number. It's called a standard reduction potential. What that does is it tells us exactly how sensitive a particular metal or an atom or an ion is to giving up electrons. In fact, every species can have both a reduction potential and an oxidation potential. But by convention, we normally only quote a reduction potential. If we consider now a metal that's common to us all, iron for example. Iron has a standard reduction potential of minus 0.44. What does that mean? Well, that number, the electrode potential, is connected to a very important property of that iron system. And that property is called the Gibbs free energy change. Every chemical reaction has a tendency to proceed up until such a point where it will be in equilibrium with its environment. And that positioning of the equilibrium is determined by what's called a thermodynamic driving force, or the Gibbs free energy for that process. The standard electrode potential for any reduction or oxidation process is connected to the Gibbs free energy for that particular reaction. So a standard reduction potential of, for example, minus 0.44 volts tells us something about the position of the chemical equilibrium for that process, and indeed just how thermodynamically favourable a particular reaction is to take place. Let me give you the example of the iron reaction on the previous slide. The reduction process for iron has a standard reduction potential of minus 0.44 volts. So how exactly is the standard reduction potential related to the Gibbs free energy change for a particular chemical process? Well, the relationship is quite straightforward. As you can see on the previous slide, the Gibbs free energy change for the process is directly related to the standard reduction potential, plus there are a couple of extra little terms at the beginning, n, which is the number of electrons involved in the process, and capital F, which is a constant called the Faraday constant. The important thing to recognize here is that when the E0 value, the standard reduction potential, is negative, then the Gibbs free energy change for a process will be positive, because the one thing that I hadn't mentioned previously, which is on that slide, is that there is a negative relationship between delta G0 and E0. That's very important because any E0 value, any standard reduction value that is positive will give rise to a negative delta G0 value. And negative delta G0 values are good, because a negative delta G0 means that the process is thermodynamically spontaneous and will occur. We can't say anything about the rate of the process because that's dependent upon kinetics, but we can say that it will spontaneously occur if a mechanism exists for it to do so. In everything that we have been looking at, and on the previous slide, and the one before that, I've been talking to you about standard reduction potentials. And you will see things like delta G0 and E0 on previous slides. What exactly does that word standard and those little symbols naught on the delta G and the E, what do they mean? Well, these numbers represent a standard situation, a standard state. And this is because reduction potentials and the thermodynamic parameters, the Gibbs free energy changes, they depend quite strongly upon the precise conditions of the chemical reaction. For example, they depend upon pressure, they depend upon temperature, and they also depend upon the concentration of ions that you have in your solution. What we do with a standard reduction potential is we stipulate the electrode potential under a fixed set of conditions. And those conditions are that reaction must be at room temperature, or 25 degrees Celsius. It must happen under a pressure of 1 atmosphere, or 1 bar, and the solution concentration of ions that we are looking at, or concerned with, must be at a concentration of 1 mole per litre. That's what's considered standard states, and all standard reduction potentials are related to those conditions. However, it may well be in the real world that the situation is slightly more complex, conditions are not standard. So how does an electrode potential change with the different conditions under which a chemical reaction might occur in practice? Well, there is a mathematical relationship between the electrochemical potential, the electrode potential, and the conditions under which a reaction is being performed. And that is called the Nernst Equation, as you'll see on the next slide. What the Nernst Equation is telling us is that the electrode potential is very closely and precisely determined by the concentrations of the reduced form of the chemical we're looking at and the oxidized form. So when we know what those concentrations are and we know the standard potential for that particular cell, then we can work out any chemical potential we need in between for any set of conditions. Why is this important? I'll give you one practical example where scientists have used the electrode potentials and their knowledge of electrode potentials to help in a real-world engineering situation. And this is to be able to protect large pieces of engineering from corrosion. If we consider an iron and steel construction, such as an oil rig platform in the North Sea, what we have is we have the metal, the iron, the steel, in contact with salt water and oxygen. All the components, all the ingredients you need for corrosion to take place. That could be a particular problem. We want these structures to be safe and sound. They need to pass certain safety regulations. People need to work on them with safety. How does one do that? Engineers make use of their knowledge of electrode potentials to do this, because what they do is they wrap around the steel a different metal which has a greater tendency to give up electrons. Remember, it's the iron that undergoes rusting and loses its electrons during that process. That's what weakens the structure. So if you place on top of the iron a different metal which is going to give up its electrons better than iron, then that particular metal is going to rust, corrode in place of the iron. And that technique is called sacrificial anodization. And what it allows you to do is to protect a particular structure. And it's extremely, extremely versatile and powerful.